This is one of a series of revision lectures from the Further Mathematics Support Programme for A-Level Mathematics. In this lecture we'll be looking at the Edexcel Decision Mathematics 1 specification, and in particular sorting and packing algorithms. The specification simply says that you should be familiar with bin packing. Now for that there are really three different algorithms that you could use. One is what's called full bin, or it's an intuitive approach where you simply put the items into the bins as best you can. Proper algorithms that come along are the first fit, where literally you take them in the order that the items are presented and fit them into the first available space. Better than that usually is first fit decreasing, where the items are first of all sorted into a descending order and then taken in that order. So what we're doing here is fitting the largest items into the bins first of all. The sorting algorithms, two types that you're expected to know: bubble sort, which is where a bubble, as it's called, moves through the list in order, and swaps of elements are made if necessary. Do be careful in questions to make sure you know whether you're trying to sort into ascending order or descending order. The second type of sort is known as a quick sort algorithm. This is where the list of items is divided at its middle point, and then those which are smaller than the middle element are written on one side of the list, and those which are larger written on the other side of the list. That obviously then depends again on whether you're looking at ascending order or descending order. The middle position is defined in the specification in two different ways, depending on whether there are an odd number or even number in the list. If the n is odd, then we can add 1 to the number, divide by 2. If n is even, add 2 to the number and divide by 2. Sometimes we think about this as producing either for an odd number of elements, it's literally the middle one, so if there are 5, there would be the middle element is the third one. However, with an even number in the list, then the middle would lie between two of them. For example, 6, it would be between the third and the fourth. So we go to the right of that. So in this specification, we're looking at the middle as being to the right of the actual center when we've got an even number. Okay, I'll now look at a number of questions which I hope will illustrate those points. The first one is about a builder, as it says, who is replacing guttering on a house, and we've got the lengths of guttering that are needed. And first of all, what we'd like to do is to carry out a quick sort to produce a list of the lengths needed in descending order. And it says you should show the results of each pass and identify your pivots clearly. Now by the pivot we're talking about this central element. So here n is equal to 10, an even number, so using the idea that if we take 10 plus 2 divided by 2 we get the sixth element. And the sixth element in this list is 2.6. So what we're now going to do is to take the 2.6 and write that in some way to show that it's in its fixed position. I normally put a box around the 2.6. Then I'm going to go through the list in order, either writing them to the left if they are larger or to the right when they're smaller. So those that are going to go to the left of the number are the 0.6, the 2.5, the 0.5, the 0.4, and the 0.3 and the 1. So those would go to the left if we were looking at ascending order, but in this question we're asked definitely to do descending order, always worth checking that. So they're going to go to the right hand side of the 2.6. The actual order that those elements appear in doesn't change, so they'll be listed 0.6, 2.5, 0.5, 0.4, 0.3, 4, and 1. So let's see that happening. And so there's our list now. Having done that, you'll see that we've got the numbers that are less than 2.6 to the right, and those numbers which are larger than 2.6 to the left. Again, the numbers in the left-hand list have not changed order, so we've got the 4, 3.2, and the other 4, same order. We now repeat this idea again. So we've got now what are called two sublists. Again, we're looking for the middle of those. So we take the left hand one, it's got 3 elements, so the middle of that is the 3.2, the second element. There are 6 elements to the right hand list, so the middle of that one is going to be the 0.4. So we write those down in boxes and go through the list exactly the same way. So there we are with the fixed numbers, the 3.2, 2.6 and the 0.4. You can see then going through the list, both the 4s appear to the left of the 3.2, they're bigger than 3.2. And for the 0.4, we've got the numbers which are bigger than it. That's the 0.6, 2.5, 0.5 and 1.0. Again, that order doesn't change, the 0.3 to the right. Now we keep doing this each time, picking out the middle of the sublists, and then sorting the numbers into order. So there we are after the next process. Have gone through the next iteration of that. You notice that we've got a sublist there of size 1, so the 0.3 immediately is in its correct position. Nothing to do there, only the 0.5 really needs anything done to it. So we're just looking at the numbers in this part of the list here to see that they are all bigger than 0.5 and so are written to the left hand side. We've now really only got one list to worry about. Its middle is 2.5, and both the numbers are smaller than that, so writing them to the right hand side. And then finally we're going to get there with our next iteration where the 1 is fixed because that's the middle of the 2, middle in inverted commas there. And so finally, of course, the 0.6 is smaller, so needs to be moved across to, in the final step, across to the right hand side. Okay, and there we are with that change made, so that we've got the list now in descending order from left to right. The marking for that sort of question, a method mark at the start here for identifying the correct pivot, and then an accuracy mark for going through and doing the first pass. That then continues with accuracy marks as you get the second pass, sorry, the next 2 correct, and then more accuracy marks for more of the rows, and then finally the final one if you've got the correct solution. So as long as everything is correct, you get this final one. So that there are 5 marks, 1 method mark, and then the rest accuracy marks. Now that sort of question often goes on to then look at a bin packing situation, which is what we'll look at in the next question. This is a question then about megabytes in files, and the files are to be stored on 50 megabyte disks. So the size of our bins when it comes to it are going to be 50. We first of all have to calculate a lower bound for the number of disks needed to store all 8 files, then use a first fit bin packing algorithm. Having done that, we need to sort the files into a descending order, this time using bubble sort, and once we've got them in descending order, use a first fit decreasing bin packing algorithm. So a pretty standard sort of question this, where we first start off with bin packing, first fit, sort them into order either using quick sort as we did in the last question, or in this particular question using bubble sort, and having sorted them, then use a first fit decreasing algorithm. So the first section then says, let's put these into bins in inverted commas of size 50. So it's worth doing this in terms of a little diagram, which is what I've tried to indicate here, and each of the packages goes in turn. In the first fit algorithm, we simply take them in the order they're presented and put them into the bin. So if this is bin 1, then the first one is 23, so I would put it in here. We don't have to be accurate, but it helps to be roughly right to make sure that you're not going to overfill a bin. So the 23 goes in there, 29 is not going to fit into that one, so it goes into the second bin. The 11, however, will fit into the first bin, so it goes in the first place available. So the 11 will fit in here, and that brings us to a total of 34. Again, just keep a check on the totals there, 34 at that point. Then come to a 34, that's not going to fit in either of the first 2 bins, so we require a third one. And that gives us 34 so far in that bin. And the next element is 10, so that one will fit into the position above the 11. So we can put 10 in here in the first bin to give us a total of 44 in that bin. 14 won't fit in the first bin, but it will go into the second one. 35 is not going to fit into any of the first 3 bins, but so we need a 4th bin. 35. And then the 17, that's not going to fit into any of those first 4 bins. So the 17, a 5th bin rather, is required. So far we've needed to use 5 bins. Now just going back to the question, the thing that we're asked to do first of all was to calculate a lower bound. Well, let's consider that now. The lower bound, we can add up all of the numbers, 23 plus 29 and so on, all the way up to the 17, and that comes to a total which we can then divide by the size of our disk, which in this particular case is 50. Now if you do that, you will find that the answer comes to 3.46. Now with 3.46, that implies that we need at least 4 disks required. So we can show that we may be able to do this with four disks. However, the bin packing that we've just done needed 5. Now this is where we come into the sorting now, to sort them into descending order to see whether the bin packing will be better when we use a first fit decreasing algorithm. Right, okay, to sort into order, then the first thing we need to do is to look at the numbers and imagine a bubble moving along the list. So we look at this bubble up here and we're going to move it from left to right at each stage, checking the numbers, the 23 and the 29 to start off with, and swapping if necessary. So on the first pass, the 29 will move to the left. So we do swap. We then look at the 23 and the 11. So the bubble has moved to here, which is now, we've got 29 and we're looking at 23 and 11. Those don't swap, so that will stay the same. We then move the bubble on to the 11 and the 34. That's going to swap, so we've got 34 and 11. The 11 and the 10, that won't swap, but when the bubble moves to the 10 and the 14, that does swap. And then again the 35 will swap, so we end up with 35 to the left of the 10. And finally the 10 and the 17, they won't swap. So the bubble just moves left to right, remembering that we're going for descending order. So hopefully if I move this down, then at the end of the first pass you can see that we've got the 29, 23, 34, 11, 14, 35, 17 and 10. That keeps happening then. We just repeat that, so that starting at the left hand side again. Now the requirement is that you simply write down the answer at the end of each pass. So just moving down a little bit more, showing you that at the end of the second pass that the 29 was obviously in its correct place. Sorry, I beg your pardon, the 10 has ended up in its correct place at the bottom of the list. The 29, the 23 won't swap, however the 34 and the 23 do. So that's the result at the end of the second pass. We keep repeating that, and at each stage you'll see that the numbers at the end of the list here are in their correct position. So these are the smallest numbers here. Just move on a couple of passes and you'll see now at the end of the fourth pass we've got the 17, the 14, the 11 and the 10 are all in their correct order. We've still got some swapping to do, and so we keep on going in the same sort of fashion until the sixth pass. They are in their correct order. However, there were some changes made between pass 5 and 6. So you'll see that at that stage in 5 we had 34 and 35, so there's been a change there. The 35 to 34 has swapped over. That was the only change at that stage, but we should now do one more complete pass where we see there are no changes. So there are no changes on the 7th pass, so we've now completed the sort. So we have our list in the order 35, 34, 29, 23, 17, 14, 11 and 10. Right, now we're ready to finish off the question now and look at the first fit decreasing algorithm. So this time we're putting them in the largest number first. So the first one goes into our bin at 35. The 34 will require another bin here, second bin. The 29, a third bin. And the 23, a fourth bin. So we've got 4 bins to start off with. However, the 17 will sit happily above the 29. Make sure you put it in the first one available. 17 is too large for 35 and it's too large for the 34, but it fits in the above the 29. 14 is the next one. That will fit in above the 35. 11 will fit in, sorry, there's a little bit of space at the top of that bin there. 11 will fit in above the 34. And then finally 10 will fit in above the 23. So there we are. We've managed to fit those into 4 bins. So you can see that the wasted space is much less, of course, than it was in the first fit algorithm. And that's simply because we have put the largest ones in first. Okay, that's the end of this lecture. There are others available for other modules and other topics in the Decision 1 module, and further information you can find on the website www.furthermaths.org.uk.